Welcome to Biogas Basics. My name is Jürgen Kube. This is part 2 of the mini-series about microbial growth. In the last presentation, we looked into the basics of microbial growth, why it's called exponential growth, how the doubling time of microorganisms is linked to the hydraulic residence time in a continuous steady-state culture, and we investigated the simplest substrate biomass model with a monod kinetic. We distinguished washout point, turbidostat, and chemostat regions, all very theoretical. In this presentation, we will focus a bit more on the biogas process and how the microorganisms in the AD process grow. One of the best ways to gather information about the microbial growth in a biogas reactor is a batch or biomethane potential BMP test. A couple of protocols have been established for those tests, most prominently the GB21 test, which is rooted in a German standard for sludge and wastewater analysis, and the VDI 4630, a standard of the Association of German Engineers for the Characterization of Biogas Feedstocks. In these tests, a sample of known mass and composition, TS and VS, is mixed with inoculum in a reactor, and the biogas production is measured over time. The gas production divided by the organic dry matter mass in the feedstock is the biogas yield. It can be plotted over time. We get a curve that looks like this. This curve looks somewhat like a first-order kinetic, although not quite like it. Let's examine the first-order reaction. The general idea is that the feedstock contains a substrate fraction. Substrate is the part of the feedstock that can be converted into biogas. The biogas yield increases as the substrate depletes. The correlation can be described as follows. The conversion rate is the biogas yield divided by the biogas potential, or 1 minus the substrate concentration S, divided by the initial substrate concentration in the feedstock SF. The first-order kinetic for a batch is ds by dt is minus k times S. K is the reaction constant and has the unit 1 over time. We can separate the variables, integrate, and insert the initial conditions. S at t equals 0 is SF. This leads to the exponential decay function that describes the substrate concentration in the batch reactor over time. We can insert this function into the definition of the conversion factor and get the final result. Y of t is y max times 1 minus exponential function of minus kt. We can use this equation to fit the measured gas production data. The fit will look like this. It doesn't look too bad, but it's also not quite right. It starts at 0, but the first two measurements are significantly below the fit. The next data points look better, but there is still a slight deviation from the fit. The reason for the poor fit at the beginning of the experiment is the so-called lag phase. During the lag phase, the microorganisms adapt to the new environment and do not grow. Lag phases often have random lengths, and more importantly, they are a function of the respective cultivation and not a feedstock or even a biological parameter. For a scale-up, especially for a scale-up into a continuous culture, the lag phase does not matter. Thus, we can shift the gas production curve by correcting the time with the lag phase, fit the BMP curve, and then discard the lag phase. When we fit the curve, we also do not fit to the first two data points. They do not matter as they are heavily influenced by the lag phase, and we exclude them from the mean squared error calculation. The resulting fit shows a lower root of the mean squared error. However, it is still not perfect. As we move along the fermentation time, the fit systematically underpredicts, overpredicts, and underpredicts again. The reason for this is that the feedstock comprises different fractions that degrade with different kinetics. We can simply duplicate the first-order kinetic and introduce two different fractions with two different kinetics and biogas potentials. The total gas production curve is the superposition of two gas production curves, one with a fast kinetic and another with a slow kinetic. We use the lag phase in the fit, but then discard it, and the fit describes the gas production curve perfectly. The concept of different substrate fractions degrading with the first-order kinetic is also used in the anaerobic digestion model 1, ADM1, which is the standard model of the AD process. I have a whole presentation dedicated to it. We have described the gas production curve with a mechanistic model and gained important information about the composition of the feedstock. Now we can use the mechanistic model and predict the behavior in continuous culture. Before we do that, I want to address empiric models. A plethora of empiric models have been published in the literature. Gompertz, logistics, and other sigmoidal functions, Richards, Transfert, Hill, and Chapman functions have been used to describe the gas production curve of a batch test. I won't show them here. They all go into great length to describe the lag and acceleration phase of a batch cultivation. The parameters often influence each other. For example, if we prolong the lag phase by shifting the curve slightly to the right, other parameters are impacted as well. Most importantly, an empiric model cannot be used to predict the behavior of a continuous culture, so don't use them. We will now use the mechanistic first-order model to scale up the results of a batch test to a continuous CSTR. Instead of initially filling the reactor with substrate and inoculum and then measure biogas production over time, we feed the reactor continuously. There is no inoculation stream, except for the beginning of the cultivation. In steady state, the digested feedstock supplies the biomass for the conversion of fresh feedstock. We assume the reactor is perfectly mixed, and the full reactor volume is used. These reactors are called continuous stirred tank reactors, or CSTRs. Unlike in previous examples, here the inlet and outlet liquid mass flows, or influent and effluent mass flows, are not the same. A significant part of the feedstock mass is converted to biogas. This can be a quarter of the feedstock mass or even more, and flow. The substrate balance contains three terms. Fresh substrate is added to the reactor with the inflow. Undigested substrate is flushed from the reactor with the effluent, and substrate is converted to biogas. The first two terms are convective terms. They are inlet mass flow divided by mass of digestate in the reactor times substrate concentration in the feedstock. The outflowing term is outlet mass flow divided by mass of digestate in the reactor times substrate concentration in the outlet. The term mass flow divided by mass of digestate in the reactor has the unit 1 over time. Its inverse is a time. For the first term, it is the inlet related, and for the second related residence time. Keep the two residence times in mind. Only one of them has any meaning, and unfortunately, most literature sources, technical rules, and government guidelines use the wrong definition. We can rewrite the mass balance using the time constants and also set the differential to 0 as we are currently only interested in the steady state. We can rearrange the formula until we get the following term. We park that for a minute and look at the definition of the conversion factor. The conversion factor is the ratio of biogas yield to biogas potential. For a continuous non-diluted system, where inlet and outlet mass flows are not substrate concentration inlet minus mass flow outlet times substrate concentration outflow divided by mass flow inlet times substrate concentration inlet. We can use the inlet and outlet related residence times to reformulate the conversion factor. The term inlet related residence time times substrate concentration outlet over outlet related residence time times inlet concentration appears in both the mass balance and the conversion factor formula. We can substitute the factor and get the definition equation for the conversion factor in a steady state CSTR. The conversion factor eta is 1 minus 1 divided by 1 plus k times outlet related residence time. The output related residence is the relevant parameter when it comes to conversion efficiency and is in fact the real residence time. The hydraulic residence time is the average time a fluid element spends in the reactor before it exits. It does not matter how fast particles are fed into the reactor, it only matters how long they stay or reside in the reactor, hence residence time. From now on, when I refer to the residence time, I mean the mass of the digestate in the reactor divided by the effluent mass flow. The factor reaction constant K times residence time is a dimensionless number, the first Darmköhler number. The Darmköhler number is the ratio of reaction rate to convection rate for the first order reaction rate or reaction constant times residence time. Now let's plot the conversion rate over the residence time of a steady state CSTR. I have chosen the reaction rate to 0.15 days to the power of -1. We get this graph. Curve here looks similar to the one minus exponential curve we got from the description of the batch experiment. It's a different experiment, a continuous culture, and has a different shape, a hyperbola. We can use this curve to estimate the conversion factor of a CSTR-type reactor depending on its residence time. For example, if we want to achieve an 80% conversion factor, the residence time must be 26 days. Or using the formula, at 30 days residence time, the conversion is 1 minus 1 over 1 plus 30 days times 0.15 days to the power of -1, or 1 minus 1 over 5.5, which is 9/11 or 81.82%. One mistake I have seen again and again is the incorrect use of a BMP test to determine target residence time in a CSTR. We can add the batch reactor to the figure. It takes 20 days in a BMP batch test to achieve 95% conversion. Ergo, the residence time of the digester must be 20 days to convert 95% of the substrate. This is incorrect. the required residence time in the CSTR will be much higher. A BMP test is a batch cultivation. The time coordinate is time since the beginning of the experiment. No substrate particles leave the reactor unless they are converted to biogas. In a steady-state CSTR, the time coordinate is the residence time. Fresh substrate particles are fed constantly into the reactor and undigested substrate particles flushed from the reactor all the time. The batch reactor shows a higher conversion rate than the CSTR, but it is important to distinguish the different time axes. For a batch reactor, the time axis is the time since the start of the experiment. The reaction is started at t equals 0 and continues to run. No new feedstock is added, no digested substrate is removed during the experiment time. For the CSTR, the time axis is the hydraulic residence time, and the curve shows the steady-state behavior, meaning that the CSTR must run for a while, typically 2 to 3 hydraulic residence times to achieve steady state. In the figure, the time coordinate for the batch reactor is the batch run time. For the CSTR, it is hydraulic residence time in steady state. The correct approach to determine the residence time of a CSTR to reach the required conversion factor is to quantify the degradation kinetics in a batch experiment with a mechanistic model, and then use the model to predict the behavior in a CSTR, projecting the desired conversion rate in a batch onto the time axis, and make that time the hydraulic residence time in the CSTR. This is really important. I have seen investors lose millions of pounds over this mistake. On a more academic note, there is one way of using a batch reactor to directly read the conversion in the continuous steady-state reactor, and that is if the continuous reactor is an ideal plug flow reactor. However, this comes with a disclaimer that there are no ideal plug flow reactors in AD. Flow reactors will require inoculation, and they struggle to keep their plug because of axial dispersion. I made a whole presentation about it. Back to the CSTR. The curve flattens towards the end. It will take extraordinarily long residence times to achieve almost complete conversion in a CSTR. In this example, it will take 60 days to achieve 90%, 126 days for 95%, and around 700 days for 99% conversion. There is clearly a law of diminishing returns when it comes to sizing reactors. Doubling the digester size will roughly halve the amount of undigested substrate leaving the fermenter. The way to get around this is by using reactor cascades. The first reactor in the cascade must be large enough to prevent a washout of the biocenosis. It should operate well into the chemostasis time, do not lead to a large change of biomass or substrate concentration. We talked about this in the last presentation. It should also be large enough to convert the bulk of the substrate into biogas. I typically aim for an 80 to 85% conversion factor in the first reactor, not because of microbial growth reasons, but for viscosity reasons to ensure that a large percentage of the degradable organic dry matter or substrate has been converted into biogas and only a residual amount of undigested substrate and the inert dry matter is left in the digester and requires mixing. More on this in the mass balance presentation series. But back to the growth of microorganisms. We notice that this cultivation has no washout point. We can lower the residence time, and while the conversion drops when the residence time goes down, it only reaches 0 when the residence time is 0. Remember, with the monokinetic we saw a washout point and a turbidostat region, so the first order model has limitations, especially at low residence times. The reaction in our first order model is substrate plus water reacts to biogas, but the correct reaction is substrate plus water reacts to biogas and biomass, and the reaction itself is catalyzed by biomass. The first order model does not model the biomass. It merely assumes that enough biomass is in the background to ensure that the reaction can progress. We learned how to get the reaction constants from a batch experiment, but is there another way to measure reaction constants, ideally in the real AD plant? And the answer is yes. We can measure the reaction constant from the dynamic behavior of the plant and its reaction to a change, or better stop of feeding, as a single primary digester with a rigid roof, for example a steel or concrete roof that is connected to the gas consumers, and post-digester via one gas pipe that comprises a flow meter. The rigid fermenter roof means that the reactor cannot store biogas, and biogas that is produced will immediately leave through the pipe and can be measured. The reactor is initially fed and then the feeding stops. At this point, the undigested substrate in the digester can no longer be washed from the system, but will be converted to biogas following the first order reaction. As the substrate in the reactor depletes, the reaction slows down and we get the characteristic decay function. Let's have a look at an example. This figure shows the feed rate in tons per hour on the right and the gas production on the left ordinate. The time axis is in hours after the feed stop. In the days before the feed stop, the digester is fed constantly with around 2.8 tons per hour. At t equals 0, the feeding auger breaks, and we see an immediate decay of the gas production. Feeding is stopped for 33 hours. Let's try to fit that decay with a first-order approach. I won't go into the details of the substrate balance now. We start with a very simple model. The biogas production, V dot, is the initial biogas production, V dot 0, times an exponential decay term, and that term contains the reaction constant. And we see that the fit is not very good. At the beginning, the real decay is faster and later slower. It seems like the gas production does not decay towards 0, but towards a positive term. Let's try this fit. V dot is V dot 1 plus V dot 2 times the exponential decay term. The first term is time invariant, and only the second term decays. This fit works much better. How can this behavior be explained? Remember, we have seen a similar behavior before, in the batch experiment. At first, the reaction was faster than the model and then slower than expected. We could explain this behavior with two different fractions, one quick degrading and one slowly degrading fraction, and we see the same split here. The biogas production term, V dot 1, here 245 cubic meter per hour, comes from the slowly degrading fraction, and V dot 2, here 321 cubic meter per hour, from the fast degradable fraction. Initially, both terms are in the same order of magnitude, but one decays quickly, whereas the other stays constant. It becomes clearer when we visualize the formula for the biogas production. The biogas production in cubic meter per hour is the negative rate of change of the substrate concentration, ds over dt, times the mass of digestate in the reactor divided by the density of biogas, to convert from kilogram substrate to cubic meter biogas, multiplied with the stoichiometric factor, 1 divided by 1 minus the water demand of the hydrolysis. The rate of substrate change is minus k times the substrate concentration times a stoichiometric factor, 1 over 1 minus w height. We set this stoichiometric factor to 1 for now. Minus, because as substrate is consumed, biogas is produced. The formula becomes biogas production is mass of digestate divided by density, times reaction constant times substrate concentration. Let's assume for a minute that in steady state, half of the biogas production comes from the fast degrading and the other half from the slowly degradable fraction. At t equals 0, both biogas streams are equal. To achieve that volume flow, either the reaction constant is high and the substrate concentration is low, or the reaction constant is low and the substrate concentration is high. The steady-state reactor contains a small concentration of fast degradable substrate and a high concentration of slowly degradable substrate. When the feed is stopped, the reservoir of fast degradable substrate depletes quickly, whereas the concentration of slowly degradable feedstock stays high and depletes only very slowly, and that is what causes the decay towards a constant gas production. The substrate concentration of the slowly decaying feedstock is almost constant, at least over a short time horizon. The fast and slowly degradable substrate will have roughly the same concentration in the feedstock, but in the reactor the slowly degradable substrate dominates because the fast degradable substrate fraction has already been mostly degraded in the steady state. We can fit the feedstock with the two-fraction model. It is almost identical to the last model, with the exception that for a long-term forecast, the biogas production will drop slightly and will eventually reach 0. So far, I've only shown the part of the experiment where the feed stops. What happens when the feeding is recommenced? To model this, we need to look into the substrate balance. Our simple models do not use the feed rate, so we need to predict the gas production as a function of the current gas production and future feed profile. We start with the substrate balance for a continuous reactor. We assume that the outflow is the inflow, otherwise the formula would get more complicated. We have used this formula before, but set the derivative to 0. Now we want to investigate transient behavior. We use the definition of the biogas production term, V dot equals K times reaction mass divided by biogas density times substrate concentration, and the definition of the biogas potential, Y max equals substrate concentration in the reactor divided by the biogas density. We assume no water uptake during hydrolysis for simplicity's sake. We can rearrange the formula to get a differential equation for the biogas production as a function of feed rate and current biogas production, which we can integrate over time. This is the result. The model overpredicts the gas production. That is not entirely surprising. One of the model assumptions is that the reactor is a CSTR, a perfectly mixed reactor. In reality, it takes a while for the fresh feedstock to be broken up and distributed in the reactor. In this example, feedstock has been fed via an auger system into a high viscosity reactor using laminar agitation. We could model the mixing behavior as well, but we are going to stop here, as we discuss microbial growth in this presentation and not digester agitation. For this, I have a dedicated presentation. Now we have two methods of acquiring knowledge about microbial growth: the batch reactor and the feed stop of a CSTR. Do they both yield the same results? The answer is yes and no. Both batch and CSTR show the same biogas potentials and substrate splits, but they also show different kinetic constants. The CSTR shows a much higher reaction constant, at least for the fast degradable fraction. The reaction constant for the slowly degradable fraction cannot be measured unless feeding is stopped for a long time, which is challenging in commercial scale biogas plants. The reaction constant has a significant impact on the decay of the gas production. This figure shows the decay of the gas production after a feed stop of the slowly degradable fraction with K equals 0.07 day to the power of -1. The gas production drops by 6.7% after 1 day. If we use the reaction constant measured in the batch for the medium fast degrading fraction, 0.4 day to the power of -1, the gas production drops by 33% after 1 day, and if we use the reaction constant for the medium fast degradable fraction measured with the feed stop experiment, K equals 2.4 day to the power of -1, the gas production drops by 92% after 1 day. When comparing multiple feed stops over a longer period, kinetic constants change slightly from feed stop to feed stop, ranging somewhere between 1 and 2.5 day to the power of -1. Let's project these numbers to a steady-state CSTR. Here are the conversion rates for the steady state. For a typical single-stage CSTR with a residence time of 20 to 30 days, the slowly degradable fraction is converted by 58 to 68%. Depending which reaction constant we use for the medium fast degradable fraction, the conversion is 89 to 92% or 98 to 99%. So which constant should be used for the reactor dimensioning? It is the larger one, measured in the CSTR with the feed stop method. But the difference for the reactor design is marginal. A conversion efficiency of around 90% compared to an efficiency of around 99% is not really impactful, especially as most AD plants have secondary digesters, which have another 20 to 30 days residence time, where the undigested remainder is subjected to another 90 to 99% conversion. The medium fast degradable fraction is converted almost completely in a biogas plant, and its kinetic constant is not that important. What is important is the kinetic constant of the slowly degradable fraction and its percentage in the overall substrate mix. So why is the kinetic constant higher in the CSTR, and why does it vary? To answer this question, we must go back to the overall reaction of the biogas reactor. Substrate plus water reacts to biogas and biomass. In the first order approach, we have ignored the biomass contribution. Substrate simply reacts to biogas, and biomass is just in the background to facilitate this reaction. In reality, some of the substrate also reacts to biomass, and this biomass must be present to catalyze the reaction in the first place. The reaction is in fact a second-order reaction. Let's start with the first-order reaction. ds by dt is minus k times s. The reaction rate depends on the first-order reaction constant k and the substrate concentration s. Here I plotted the conversion factor for a CSTR following a first-order reaction. Second-order reaction looks like this. ds by dt is minus k prime times biomass concentration, x times substrate concentration s. I use k prime to denote the second order and k for the first order reaction constant. They have different units. The unit of k is 1 over time and the unit of k prime is 1 over concentration and time, for example, tons per kilogram in day. We also have to balance the biomass. The biomass production is the substrate consumption times the yield coefficient yxs, or dx over dt is yxs times k prime times x times s. We assume here that there is no water incorporated in the biomass during its production. The term biomass comprises acidogenic, and methanogenic microorganisms. How can we compare the second order to the first order reaction constant? Well, we know that at high residence times, when the conversion is almost complete, the biomass concentration is the yield coefficient times the feedstock biomass concentration SF. We can insert this maximal biomass concentration into the second order reaction to come to comparable terms in the substrate balance that only depend on the substrate concentration. So, K prime is K divided by SF and YXS. Let's plot the conversion factor in a CSTR for the second order reaction. The dashed line is the second order reaction, the solid line is the first order reaction. We see that in the chemostat region, at high residence times, the second order reaction behaves very similar to the first order reaction. But unlike the first order reaction, the second order reaction shows a washout point. The second order reaction can describe a CSTR much more accurately than a first order reaction. However, it requires knowledge about yield coefficient and initial biomass concentration in batch reactors. For normal AD plants that operate in the chemostat region, using a first order model is often good enough. Only when we need to consider the impact of the biomass concentration, for example at low residence times, in dynamic situations, or in systems with fluctuating substrate and biomass concentrations, a second order approach can be useful. So how can a second order kinetics explain the higher observed first order reaction constant in a CSTR after a feeding stop compared to a batch BMP test? The biomass concentration in a batch and continuous reactor are different. The batch reactor is diluted with inoculum. The inoculum is selected to have a minimal intrinsic biogas production itself. It has been taken from another reactor and has been transferred to the lab. Sometimes it is screened, and often it is starved to reduce its biogas production. In a continuous reactor, as in the CSTR with the feed stop method, the inoculum is at the steady state concentration, and it has not been transferred to a new environment. In a batch experiment, the biomass concentration is lower, and thus the observed pseudo-first order kinetic constant is lower. In a CSTR, the biomass concentration is higher and the observed pseudo-first order kinetic constant is higher. Unfortunately, the transfer of a second order kinetic from batch to CSTR is not that simple. Unlike the first order reaction, the second order reaction depends on the actual substrate and biomass concentration in the reactor. And while the substrate concentration can be estimated from the biogas production, the biomass concentration is more difficult to model. For a CSTR, at high residence times, the substrate demand for the metabolic maintenance and the decay of biomass must be considered, which complicates the biomass balance. I try to avoid complicated models as they require many parameters, which often cannot be measured independently and have mostly only academic value. For a parameter fit, I would simply use the initial biomass concentration as another model parameter. Before I conclude, I would like to compare all kinetics that we have discussed so far. Here, I show the gas production curves in a batch experiment for all kinetics. The abscissa shows the time since the start of the fermentation, and the ordinate is the conversion factor, which is 1 minus substrate concentration divided by initial substrate concentration, or the biogas yield, divided by the biogas potential. Top left is the classical first-order reaction. I have excluded any lag time here. The reaction rate slows down as the substrate depletes. The substrate consumption rate is directly proportional to the substrate concentration, the hallmark of an exponential function, and this gives the exponential decay function. Bottom left is the superposition of two first-order kinetics, a medium-fast and a slowly degradable fraction. This behavior can be observed in most BMP tests. Compared to a single fraction first-order kinetic, the two-fraction gas production curve shows a faster rise at the beginning of the experiment and a slower rise towards the end. The gas production does not seem to reach a plateau, instead the sample continues to produce a small amount of biogas. The top right curve shows the gas production of a second-order reaction. The second-order reaction looks very much like a first-order reaction, but if the initial biomass concentration is low enough, it can also model lag and acceleration phases. At low initial biomass concentration, substrate is consumed but biomass is built up, so the reaction rate seems to be almost constant, leading to a sigmoidal or linear gas production. Overall, a second-order fit requires more parameters than a first-order fit, and information about initial biomass and substrate concentration and the yield coefficient are required in addition to the reaction constant. For completion, I show the monokinetic in the bottom left figure. I explained the monokinetic in the previous presentation of this mini-series. The monokinetic should be used if the hydrolysis is not the limiting step of the biogas production. For example, when the substrate are volatile fatty acids, glycerol, or oligosaccharides. The monokinetic is usually much faster than a first or second order kinetic. It is characterized by a long, almost linear stretch in the gas production curve. Remember that at high substrate concentration, the monokinetic is essentially a zeroth order kinetic and the reaction rate is constant. A monokinetic can also be used to model a mass transport limitation, which is also a zeroth order reaction, for example digestion of fat. Like the second-order kinetic, it relies on several parameters: initial substrate and biomass concentration, μmax, or minimal doubling time in free growth, and the mono constant. And here are the same plots for a steady-state CSTR, a reactor that is continuously fed and which has a continuous effluent stream. This time, the abscissa is the hydraulic residence time. Top left shows the first-order reaction, single fraction. Bottom left, a first-order reaction with two substrate fractions. The first-order reactions do not show a washout point and have a non-zero conversion at very low residence times. Top right shows the second-order reaction. It has a washout point but approaches a first-order reaction for higher residence times. The bottom right reaction is the monokinetic. It has a washout point as well, and the conversion curve is much steeper near the washout point, which explains the turbidostat region, where a small change in residence time has a significant impact on the substrate conversion. At higher residence times, the conversion is almost complete. In the chemostat region, small changes of the residence time have almost no impact in substrate conversion and concentration. Monod kinetics are prevalent in wastewater fermentations where no significant hydrolysis is required. I did not develop all the formulae for the curves shown here on screen, as this would probably bore most viewers. If you want to dig deeper into modeling of batch and CSTR reactions, pause the presentation now for the necessary formulae. Let's recapitulate. To gain some inside knowledge about microbial growth, we start with the batch test, also called biomethane potential, BMP, or biogas potential test. Here, substrate is mixed with inoculum and biogas is produced. If there is enough inoculum, the resulting biogas production follows a first-order kinetic. Often, the biogas production can be better described with the superposition of the degradation of two substrate fractions, a medium-fast and a slowly degradable fraction. The two fractions have different potentials and different kinetic constants. For example, the medium-fast degradable fraction can be starch, hemicellulose, protein, or pectin. The slowly degradable fraction is typically lignocellulose. Sometimes we still encounter a short lag or acceleration phase, which we can exclude from the model by shifting the time coordinate by the lag time and ignore the first measurement points. The length of the lag phase is a property of the specific batch trial, and it can even vary between different trials in a triplicate experiment. The length of the lag phase is not even of academic interest. It is merely used to achieve more accurate fits of the kinetic constant and gas potentials. Do not use empiric formulae to fit batch experiments, as they cannot be used for projection of the conversion factor in a CSTR. Use a mechanistical model instead. A widespread mistake in the biogas industry is using the time since the start of the batch experiment as equivalent hydraulic residence time in a CSTR. This approach is wrong and underestimates the required hydraulic residence time. For example, a batch reactor that shows 90% conversion after 30 days has a reaction constant of 0.077 day to the power of -1. A single-stage steady-state CSTR must have a hydraulic residence time of around 117 days to achieve the same conversion factor with the same reaction constant. The reason for this is that a CSTR has a continuous stream of fresh feedstock entering the digester and a continuous stream of undigested substrate leaving the reactor with the effluent. The batch reactor can be modeled with an exponential function, whereas the CSTR is modeled with a hyperbola, which converges much slower towards full conversion than an exponential function. Another way of estimating kinetic constants is a feed-stop experiment, where a CSTR operates at steady state and then feeding is stopped and the decay of gas production is monitored. The decay of gas production follows a first-order kinetic, and we can observe much faster kinetics in the CSTR than in a batch reactor. Often, the gas production does not decay towards zero, but towards a constant value, which is the gas production from the slowly degradable fraction that decays only very slowly and thus seems to be constant during a short time horizon. When feeding is recommissioned, the gas production response is overestimated because mixing effects play a role in commercial scale applications. The high reaction constant in commercial scale digesters is good news for the design of AD plants. The reaction constant of the fast degradable fraction is so high that this fraction degrades almost completely in the primary digester of commercial AD plants. The mass percentage and the reaction constant of the slowly degradable fraction is more important for the reactor dimensioning. The different reaction constants in batch and continuous fermentation can be explained with a second-order approach, where the reaction rate depends not only on the substrate, but also on the biomass concentration. The biomass concentration in the CSTR is higher than in the batch, which requires external inoculum, and thus the observed reaction rate is higher. The first order kinetic is ds by dt equals minus Ks. The second order kinetic is ds by dt is minus K prime, times biomass concentration, x times substrate concentration S. Both biomass and substrate must be present to produce biogas. The biomass concentration can be pulled into the reaction constant to create a so-called pseudo-first-order reaction. That is what we observe in batch tests and after a feed stop. We can convert one reaction constant to the other if we know the initial substrate concentration in the batch or feedstock substrate concentration in the CSTR and the yield coefficient YXS, which is the ratio of biomass produced to substrate consumed. Because the biomass concentration is higher in the CSTR at the start of a feed stop than in a diluted batch reactor, the observed reaction constants in the CSTR are higher. Unlike the first-order approach, the second-order reaction also shows a washout point, whereas at higher residence times, in the chemostat region, it behaves very similar to a first-order reaction. Often, the first-order approach is good enough for reaction modeling. It requires fewer parameters than the second-order approach. I finished this presentation by comparing first-order single fraction, first-order two fractions, second-order and monod kinetic in the batch and steady-state CSTR. Select the appropriate model for the task ahead. This concludes the second part of the miniseries about microbial growth in the biogas reactor. I see you in the next episode of Biogas Basics, where we will address the inhibition and limitation kinetics that mostly affect the methanogenic microorganisms.